Okay. So in previous lecture, we started on the function of a multivariable. Okay. So multivariable functions. One way we look at it is basically multivariable function. What's going on? It's a function of multivariables. So you have a number of inputs, okay, and then you have one output. If you think in terms of system point of view here, right? Yeah. Most of the time, what we're interested in a function, for example, function of two variables, okay, and we probably also look at function of three variables. Okay, so this is most of the time we're going to deal with. Okay. And for function of two variables, what I need you to be ready is, for a typical function of two variables, you should be able to draw it out. Okay, so basically you know what it looks like in 3D space. So essentially, how do you visualize it? Okay, for typical ones. Typical ones means such as z equal to, for example, 3x plus 2y, or maybe plus 4, like this kind of case. Okay, so you know what this is. This is a plane, right? This is a plane here, and maybe it will be like this. So z equal to, like in the previous lecture, we have illustrate slightly different. We have this. Let's, for example, this one is z equal to x squared plus y squared. Okay, so this one here you will come across quite a bit. This is what we call paraboloid here, right? Essentially, when you draw it out, you see z equal to x squared plus y squared. The right side is x squared plus y squared. That means z must be always greater and equal to 0, right? Yeah, because this is positive. So the minimum point is 0 and is always positive. And also, okay, as we can learn today, let's just say if you let z equal to anything, to a number, that's 3 or 4, what would that give you? 3 equal to x squared plus y squared, or 4 you put x squared plus equal y squared. That gives you what? A circle, right? Yeah. So it's actually what we call basically a paraboloid. Okay, it's basically a shape like this. Okay, so being able to draw this out in the future, particularly in the future, will help you quite a bit in understanding some other operations. Okay, so this is a paraboloid here. Okay, yeah. So then you probably will see now, if this is a negative x squared plus y squared, so basically put a negative sign here, and guess what? It's going to be, right, inverted over here. Okay, yeah. So this is what I mean. What basically you would be able to do given this kind of a graph here, right? Now, just one more here. Let's just say if I have a z equal to 1 minus x squared minus y squared. This is what I showed you in the previous lecture. Okay. So what would be the difference between this one and this one now? Yes, right? Basically, raise the red one by 1 unit here. Okay. Yeah. So, like this kind of thing, it's very helpful if you can draw it out, right? Just to illustrate. Okay. Yeah. Was that good? Yeah. So that's the kind of things that you will see. Okay. Yeah. All right. So besides drawing it out, visualize it. So this one you can visualize because this is a function of two variables. So you can visualize in 3D space, but this one you couldn't. Okay, you can't. Okay. So beside the drawing, this is what we call a surface here. Okay, this is called a surface. Besides drawing it out, we have another way to illustrate this kind of function of two variables. Okay. Yeah. The other one is what we call a so-called contour plot. Okay, so this is you can call it surface plot basically. Okay, that's as usually more straightforward. The other one is called contour plot. Okay, so what's a contour plot then? For example, okay, so this is a z equal to negative y. I showed you in the previous lecture. This is a plane. Okay, this is a plane here. So contour plot, what happens is this is z equal to f of x y here. Okay. So what you do is you let the z Okay, let z equal to a constant. Okay, that is a constant. We don't know what a constant is, just a arbitrary constant. Then what you have now is f of x, y equal to c, right? Yeah. So let's come back here. When you let z equal to constant, think in a 3D space, okay? When you let z equal to constant, it's actually in 3D space, it's not a constant. In 3D space, it's actually referred to a what? To a, sorry? Vector? No. To a z equal to constant in 3D space. It's plane, right? It's a plane parallel to the xy plane, basically z constant. So this is the plane z equal to negative y. And then when you let z equal to constant, it depends on what the constant c is. And basically, here is z equal to constant. Maybe this is one c. That's another one c, right? Another value for the c. So look at that. Then between the plane z equal to negative 1 and the z equal to c, you got what? You got an intersection here, right? You got an intersection. That intersection, okay? So that intersection is basically going to be part of this contour plot. Was that okay? Where the contour plot is from. So you project those basically intersection, okay? Project the intersection into the xy plane, okay? Into the xy plane. And this is what you get here. Okay? So in this particular case, when you cut basically z equal to c, it's like a cutter, okay? It's horizontal cutter. So you cut, cut everything using this z equal to c, the horizontal plane. And it depends on what the surface is, you will end up with a certain curve. And in this particular case, you end up with a straight line. And that straight line, why is it straight line? Because if you let z, for example, if you let c equal to 1, okay? So what do we get? We end up with a negative y equal to 1, or y equal to negative 1, right? And what's y equal to negative 1? That's y equal to negative 1 is here, right? That's a straight line, okay? That's a straight line here, okay? So this is a whole bunch of lines that you got by giving c different values, all right? Yeah. So this is a level curves, and then you put everything, basically drop all the curve, the intersected curve, into this xy plane, and this is your cluster. We call it basically, it's a cluster, okay, of curves, okay, or what we call is a level curves, okay? It's a level curves. So why is it level? Because, at a different c, essentially, okay? At a different c there. See, for example, if I give you another one here, so this is basically another type of curve. So z equal to y minus that, that's what we just mentioned that. If you cut this one, use different, right? You let z equal to c. You cut this one with a different z equal to c. For example, if c equal to 1 or c equal to 5, right? Actually, c is not going to be 5. C negative 1, negative 5, for example. Okay? Yeah. So what do we get? When c equal to negative 1, what do we get? We end up with 1 minus x squared plus y squared equal to negative 1. So that gives us x squared plus y squared equal to 2, right? Equal to 2. And this one here will give us x squared y squared equal to, so negative equal to, this whole thing equal to negative 5. 5 over there, so 6, so that's a 6, right? 6, okay? Yeah. So basically, this is a circle, right? It's a circle, yeah. And this is what happens here. You have a cluster of circles, okay? After the plotting out, right? Yeah. So here's a little sort of animation here. This is what happens when you cut it, right, with the surface. You got different intersected curve, right? And we're not looking at the cutting this direction, only horizontal direction here, okay? Yeah. All right. So now, basically, the question is, what does the level curve do? Okay, what kind of what good does it do to us, right? We will use that in the future lectures. But this is one quick example of how a level curve, okay, can be used, okay, to illustrate the idea of a surface. So this is a hill, okay. You're cutting the hill with the horizontal, basically planes, and you end up with a cluster of level curves, right? Yeah. So if you look at this whole bunch of cluster level curve here, now what information does the level curve can tell you about this the mountains you're climbing here? And of course, you can label each one of them with a certain altitude, and you know that's altitude, right? Yeah. And what else could it tell you? If you look at this one here, well, what does it tell you this side and this side here, based on the spacing? Steep. Yeah, slope, right? Yeah. So basically, this side here tells you it's steeper, right? But this side is not. Okay. But the question is, if the people would ask you, so what exactly is the slope on this side? Exactly, so the level curves won't be able to tell you that. Is that right? Yeah, so that only gives you a so-called qualitative kind of idea. Okay. So only give you this qualitative information on slope. Okay, on slope. Okay. But if you need quantitatively what's the value on the slope, that's what we're going to cover in the next lecture. Okay, we're going to have those so-called gradings. Okay, to get, actually we also have one called directional derivative to get the slope of a mountain, of a surface, okay, in any direction. Okay, that's level curve. Was that it? Yeah. Now, this is a level curve only works for function of two variables, right? Yeah. So I do mention that. What about the function of three variables? Let's see if I have a function of three variables. So let's just say I have this function. Maybe I have a function of three variables like this. Okay? Yeah. So we said we can't visualize this in 3D space, right? We can't visualize that. But we can use the similar idea as this contour plot or the level curve idea to visualize this function at here. So what does the level curve or what does the contour do? Contour plot do? What you do is you let the z, right, equal to c, right? You let the z equal to c, and then you look at the level curves or to contour plot. So for this particular case, what we can do is we can let w equal to c. Okay, w equal to c. If I let w equal to c, then what do I end up with? For this particular case, I end up with a c equal to x squared plus y squared equal to z squared, right? Yeah. So now, if in general, this is basically a function of x, y, z. Okay, x, y, z. Okay. So instead of here, there are 4 different variables. But now instead of 4, when we let the w equal to c, we end up with just what? 1, 2, 3 variable now, right? 3 variable. If just a 3 variable, guess what? We will be able to visualize that in 3D space now, right? So for this particular one, and if you take a square of both sides, you end up with the c squared. Okay? Yeah. So if you give the c a certain value, okay, if you give c a certain value, what will be this guy here? What will be the surface for this? What does this surface? Sphere, right? Yeah, this represents a sphere. So you give c value, you have a sphere. You give c another value, you get another sphere. So basically, you get a layer and a layer of surfaces, right? Layer and layer surfaces with the different value of c. So that's what we call, basically, the other one called level curve. So this one we're going to call it what? Level, okay, surfaces. Okay, level surfaces. So different c value, you get one layer of a surface. Another c value, get another layer of a surface. That make sense? Okay. So now you can, when you're having this function here, So in your mind, you're not visualizing it, but you can sort of establish a certain idea. Oh, this guy here, it's layers and layers of surfaces, right? Given different given different W value at here. Okay? Yeah. That's what happens. So essentially, just understand the geometrical meaning and where this, and also the previous one there, how do you get the level surface and how do you get level curves? All right. So understand the geometrical meaning right here. Okay. Yeah. We will use them in next lecture. Okay. We'll use them in next one. So probably not today. Okay. Any questions? It's all good? Yeah. So now let's continue, which is the second part here, multivariable calculus. So now we have introduced a multivariable function. So we need to learn how to do calculus with multivariable functions. Okay. Okay, so let's start from the very basic ones, a single variable calculus. Okay, yeah. So if you remember, when we have a single variable function, and when we trying to take the derivative of that, and the definition of that is what is okay. You give the x and small increase. Okay, then you minus the f of x, then divided by delta x, and you let the delta x go to 0. Okay, so that's the definition of derivative, right? df over dx. Okay. So if we're having as a multivariable function, so I'll use a multivariable function of 3 variables as an example. Okay, so let's say if I have this one here. Okay, given this f of x of z, and I wanted to take the derivative now. So this is the derivative of x, but now you have 3 different variables. So when you take in this particular the derivative, actually are going to be with respect to x, with respect to y, or with respect to z. So the writing here now is this now. So this writing. Okay, so this is the thing here. So remember in the first lecture, I mentioned about the journey of a calculus from this D to where? To this. Okay? So this is basically half of the starting of the half journey here. Okay? And then we'll end up with where? It's here. Okay? Yeah. The inverted triangle. Okay? So right now we're coming into this. So this is called a curl D. Okay? So this guy here is called curl D. Okay, it's a curl D. Or curly D, doesn't matter. Okay? Yeah. So basically it's not straight. Okay, so this is how you write. Okay? Yeah. And when we write it, I call it basically I sometimes still call it df over dx. Okay, more precisely it should be called partial f over partial x. Okay? Yeah. So that's called partial derivative now. Okay? Partial derivative. Why is it partial? Because we have 3 different variables, x, y, z, right? So we're taking this derivative is only with respect to x. So that's why it's called partial derivative. Okay? Yeah. So what's the definition for partial derivative then? Very, very similar to single variable function. So single variable function, you have a delta x go to 0, right? So you still have it here, okay? And you have the incremental of this x quantity by delta x, okay? Y, z, you keep it there, minus f of x, y, z, and then divided by delta x. Okay, so that's the definition of this partial derivative. Okay. More precisely, in this particular case, this is a partial derivative with respect to x. Okay? Yeah. Okay? Now, the next question is, given a multivariable function, how do I calculate this partial derivative? So it all comes out of this definition. All right? So if you look at the definition here, look at this numerator. When you use this minus this, what's changed? What's not changed? X changed, right? Does the YZ changed? No. Okay? So basically, when you're taking partial derivative, when you're taking partial derivative back to x, you're treating every other variable as if they are constant. That's just as simple as that. Just remember this one simple rule. You won't get wrong with the partial derivative. Okay? Yeah. So basically here, treat every other variables as constant. Okay, as constant. As constant means what? It's a 3 or 4. So I find in the past that lots of people, when you have all x, y, z mixed together, even though that you know the rule, but sometimes your eyes is fooling you. So what happens is, sometimes if you feel like you like a real constant that much, you can replace the y to z with a certain real constant, 3 or 4, but just temporarily, right? Just temporarily. Then you replace it back afterwards. Okay? Yeah. Okay? That's what happens here. Similar definition can be written for df over dx. Okay, basically you know what to do, right? Yeah. Okay, good. So, and for this particular one, this is what we call the first order partial derivative. Okay, so this is basically a couple of notation here. This is a first order. Okay? It's first order. Okay? And we also have higher order. So for example, we can take a second order partial derivative with respect to x. So what does this mean? This basically means this. Okay, this basically means this. Sorry. Okay, so you take partial f over partial x first. Whatever the result set here is, then you take another partial derivative, based on this result set here. Yeah.
Is that the only way to write a partial derivative?
You mean partial f over partial x?
Yeah.
Yes. That's the only way, actually.
There's no, you have to do like prime or anything?
No.
Okay.
Very good. Yeah. So in this particular case, there's no prime. Okay. The prime thing only works with a single variable. Okay. Good point. Okay. Yeah. Yeah. So often in time, this is where things could get pretty ugly, especially when you have a long expression with all these curl things going around, right? Yeah. So if if this one here, you probably will see that in my lecture notes there's slightly different notation. Sometimes I also write this fxx. Okay, so same thing. Okay. Sometimes it could. This is kind of rare. This could also mean this. Okay. Yeah. What I would suggest at this stage is the order when you're taking partial derivative. This one actually. It's kind of easy to understand. Okay, second order. Basically, this means take this partial derivative first, and then take a partial derivative back to the results. Okay, add here, and is x. Okay? Yeah. So if you have this kind of notation, so basically df, like this. So df squared, second order over dx over dy and then dx. So this is still second order. But for this one here, what this means is this. So d over dy and df over dx. Okay? So you may wonder, why could it be d over dx first and df over dy here? Okay, but technically, very precisely, when you write this dy at here, dx here, your first partial derivative is with respect to this one here, okay? So this. And this is the second partial derivative, okay? That's where this is from. Was that good? And the other notation, this is basically writes as fxy, okay? Fxy. Okay. So the first subscript x right here, that's your first partial derivative, okay? And then you take the second one with respect to y. Okay? Yeah. Now, because actually I will show you, okay, in the next is these two technically they are not the same, okay? Technically not the same, but okay, under certain situations, okay, these two, okay, will be the same, okay. Is that okay? Yeah. So you could have a third order, but just keep going according to this fashion right here, right? Yeah, in this fashion. So the question is, under what situation that these two are the same? Okay, when function f is a very nice function, okay, and then fxy equal to fyx, okay, yeah. So what's a very nice function? Basically, it's a smooth. Okay? Yeah. There's no sharp interactions, with sharp change in the middle of the somewhere. Okay. Yeah. So fortunately, every function given you will be nice function, right? So, but if you study math major, then you should know that technically they are not the same thing. Okay. Yeah. Okay, so now we're ready to do some partial derivative. Let's look at some examples. Okay. When you do partial derivative, just bear in your mind that the simple rule that I just mentioned. Okay, treat every other variables as if they are constants. Okay. So here's f here. What's df over dx? Okay. Yes.
What's that last, yeah.
2z. Yeah. Kind of hard to distinguish my 2 and z. Yeah, 2z. Yeah. Okay. So first, look at what variable you're taking partial derivative with respect to. It's x. So you treat y and 2z as if they are constant. So basically you're taking partial derivative like this. Okay, like this. X squared bracket y plus 2z. So what do you get? 2x times okay, 2z. Yeah. How about partial derivative? So I'll just let you be comfortable with all different kind of notations. What about this one here? This means partial derivative with respect to y, right? So this is where sometimes you could get a little confused, with all the x and y's mixed together, right? Yeah. So what will be the result here? X squared times 1 plus 0, right? Yeah. Okay. Was that okay? Yeah. Well, you may have done differently. What you do? You probably expand it, right? That's okay. Yeah. So practice this. What about f of z? You treat, when you're taking partial derivative z, you treat x and y as if a constant. So constant means the derivative of constant. The derivative constant with respect to z will definitely be 0, right? It would definitely be 0. So in this case, you get what? 2x squared, right? 2x squared. So this lecture will do lots of derivatives, okay? A lot of derivatives here. So keep a clear mind, okay? So let's try this one. Let's see another example. And fxy equal to y sine xy. Okay? So it's getting a little bit complicated. What is df over dy? Okay, what's df over dy? Okay, so this one will give you 1 minute. So df over dy, you treat x as a constant, but there's a sign there. And there's a multiplication, so so anybody able to get an answer? Let me see.
Sine xy
Sine xy, and sorry, what's the other one?
plus xy.
That's right. Yes. Okay. Is that the only one answer I could get? Anybody got the answer? Anybody got an answer? No, not necessarily the right one. Yeah. You got something there. Okay. So. Here actually involve a couple of very basic elements here. So you got two multiplications here, I guess. It's like a u times v, right? Derivative, and then you have to use which rule? Product rule, right? So for using product rule, so I'm going to write all the details out here, okay? So sine xy. So you're taking basically partial derivative like this. There are two parts, so I'm going to use product rule. So the derivative of the first term with respect to y times the second term. The first term times the derivative, the partial derivative of the second term. Okay? Is that clear? Yeah. So first one here, what's dy over dy is equal to 1. So that's sine xy, right? And second one here, this is d over dy sine this. And sine, this is actually a function xy here. So I guess what you need to do is, if you prefer, you can use another chain rule here. You can maybe, for example, you can let u equal to xy, right? And then you can basically carry out that calculation. But in this particular case, this is basically cosine, derivative sine first. Okay, you get cosine, right? Derivative sine first, you get cosine. And then the partial derivative of what's inside the bracket of a sine, right? Yeah. So partial xy over partial y. So that x is constant, so it's basically end with x only. Okay? Okay. So this is where the answer is from. Okay? Yeah. Was that good? So you just have to keep a very clear mind of what you're taking, the derivative you're taking respect with, okay? And otherwise, things could go mixed up. Okay, any questions? Yeah? Yeah. Okay. So now I'll let you we'll see that what is the geometrical meaning? Okay, what's the geometrical meaning for a partial derivative? So for example, we're giving a function f, and we're taking partial derivative of f with respect to x. So let's just say I'm going to use a function of two variables, for example, okay, for illustration point of view, because it's three variables we want to be able to illustrate. And if we're interested is, okay, and I'm going to plug in certain values, okay, certain x naught, y naught into the end results at here, right? Yeah. Okay. So what's the geometric meaning of this, or partial f over partial y? Okay. What we can do is, okay, let me arbitrarily draw a surface first. So let's just say you have a function of this, right? You have a function of x, y. And we know this one is a surface, okay? So for example, maybe the surface, okay, look like this, okay? That's a surface, right? That's a surface, okay? Okay, so this is a surface out here, and partial f over partial x like this. If I use my definition, okay, so this is if I use my definition for the partial derivative, okay, guess what do we have? We have the definition limit, right? Limit, what do we get? The used to be x, but this is x naught now, okay, increased by this, and y naught. F and x naught and my x naught y naught and over delta x, and delta x goes to 0, right? Goes to 0. Okay? Yeah. That's the definition partial derivative, right? Partial derivative. And this is more precise. This is a partial derivative at specifically a location x naught, y naught. So maybe x naught, y naught is here. Okay, it's here. Okay, all good? Yeah. So, let's examine this definition again. So when we look at the definition right here, this function minus this function, or this value minus this value. What is not changed? Y naught. So basically, you have a constant y naught here, that's not changed. And what is changing? You are basically changing what? You are basically increasing the x naught by how much? By delta x, right? But bear in mind, you're not changing y naught. In other words, so I'm going to basically exaggerate it here. So basically, what are we doing? We're walking along a line like this, right? And what's this line right here? It's y equal to y naught. That makes sense? So when you're changing around this point in here, like this, okay, like this, only increasing the x naught without changing y naught. So that's the kind of a change we're looking at here, right? Yeah. So imagine, right? Imagine there is a little guy walking along this line right here, and then there's another one right at the top of this dummy here. Okay, so this one here is what? Is the z naught equal to f of certain value x, y. Okay, not necessarily z naught, but just z equal to f of x, y like that. Right? Yeah. So as this is walking right here, and that one is automatically walking along the surface, right? And guess what's going to happen? There's going to be a curve traced out, okay? There's going to be a curve traced out along the surface. So that surface, that curve, right, that curve is actually, more precise, is actually what? It's actually the intersection between which one? Between this plane, right? Between this plane and this surface. Does that make sense? Yeah? So that's the curve is traced out by this, right? It's this. Okay? So now back to this partial derivative. We're talking about partial derivative around x naught, y naught location. Okay, x naught, y naught location. And where is x naught, y naught? So basically that might be corresponds to this location at here, right? This location. So we're considering y naught here. This is a constant, right? This is a constant, not changing. And forget about the multivariable function. What does the single variable derivative give you? Slope, right? Give you a slope. Slope of the curve. So this is a partial derivative, even this is partial derivative, but we're really considering this just a derivative, right? Derivative in this direction walking. And this is basically, right at this here, the partial derivative refer to what now? To the slope of this curve. At where? At this location. Okay? So if you draw a line, okay, which is tangent to that point, that slope, okay, for this line is given by this quantity. Okay, that's the slope, okay, of that particular line. Okay, yeah. And what's and then the other concept, remember, where is this curve from? That curve is from intersection of the plane y equal to y naught and the surface z equal to f of xy. Okay? Yeah. So partial derivative is a slope concept. Okay? So similarly, you can think of a partial derivative of this one, right? With respect to y. Okay? With respect to y. So can you draw now what slope does this one represent now? Yeah, it's the slope for a certain curve, and that curve has to be intersection between which plane now? Between the plane, which plane? So see, this is the slope for this curve, right? For this curve at this point. And that curve is the intersection of plane y equal to y naught and the surface, right? So for this one here, this got to be the slope of curve of, let's say, intersected curve. Okay, intersected curve between what? Got to be the surface and what else? X equal to x naught. Okay, between these two. Okay, and at x naught, y naught location. Okay? Yeah. Because we have this one here, right? If you're talking about general ones without x naught, y naught, right? You know, it's just a general and then it's a certain value of x. Okay? But this is specifically like this. Is that good? That's the geometric meaning. Okay? So slope concept. Very important. Understand this slope concept, okay? Yeah. So just one small step extends forward here, okay? Just one small step. Maybe let me just not messing it too much. Maybe let's just arbitrarily sort of illustrate the idea here, okay? Okay. This is another plane at here. Okay, this is another plane. For this plane, you will have intersection, okay, like this, okay, and at that particular location, you would have another slope, okay, like that, okay, of line for this, right? Yeah. So recall that when you have a single variable, here's a curve, right? This is a curve, and maybe this is x naught. Then how do we approximate this curve at x equal to x naught location? What do we use to approximate this curve at x equal to x naught location? What did we use? You know, you're doing numerical analysis, right? So how do you approximate the curve at a certain location? Times x naught. You can use what? You can use a straight line, right, to approximate that curve around certain location. That make sense? Yeah? So now, back to the surface now. This is a curved surface. Okay? At this location here, okay? If for a curve, I can use a straight line to approximate it. Then for a surface, if I want to approximate the surface, I can simply use what to approximate it?
Tangent plane.
Tangent plane, exactly, right? That's a little dramatic, but you like straight line, you like a plane, right, instead of a curved. So that's basically the idea here. Now, if we're thinking in terms of plane to approximate this surface, remember, what determines the plane? You need a point on the plane and what?
Vector perpendicular.
Perpendicular, right, to the plane. So, where would that perpendicular vector from? You have what? You have one tangent here. You have another tangent here. So basically, we'll see that in the future. This is just for concept-wise. You can construct actually what? Two vectors, right? Which is the tangent vectors at that location. Then you can do a cross product of the two vectors, then you get a normal vector. Does that make sense? Yeah. That normal vector can be used to construct the tangent plane. Okay? Yeah. So trust me, everything's going to be coming together, okay? Particularly at the last lecture. So you gotta come to the last lecture though. Seriously. The thing about this course is the last lecture is the highlight, is actually. Okay? Yeah. Okay, so let's look at an example now. Okay. Okay, let's look at example. So now we understand the geometric meaning now. Okay, let's look at one more example right here. This is a 1 year's midterm exam. Okay. We have a f of xy equal to this, and it's arctan y over x. And I want you to calculate second order of this and the other one like this. Okay? Yeah. Okay, that's one of the midterm, I forget, a couple of years ago. Okay, and lots of people flunked in this question. So usually I give you a hint. Give you a hint. So the hint is tangential. So basically the derivative of this one give you this. Okay? Yeah, that's a hint. Okay, so with the hint, okay, let's just see what's going to happen here. You're taking second order partial derivative. You can't get second order immediately, so you have to take a first order first, then you take another one to get a second order, right? Okay? So you've got to do this first. So this is where you need a simple rule again, that so-called chain rule. Okay, a chain rule here. So this chain rule is like this. If you have a function of for this particular one here, okay? When you have a function of x, y, let's say a function of u. Okay, so f is a function of u, and u is a function of x, y. Okay, u is a function of x, y. Okay. So then I want to get, okay, when you plug the u into f, that's multivariable function. And you want to get partial f over partial y. So the chain rule apply is, you got to take the derivative of f respect to u first. But you look at this one here. If just f of u, that's actually what? A single variable function, right? That's a single variable function. So you don't need to use that partial d. You can use a straight d out of here. Okay, df over du. Right? Yeah, because f is only a function of u only. Then this partial u over partial x. Okay? Is that clear? Okay? Yeah. Alright, so now let's use this rule for this question in here. So what is my u at here? So u equal to what? Y over x. Okay? Y over x. Then partial x over partial y according to this rule is a df over du times partial u over partial x. Right? Okay? So, can you write down the next step? Okay, so what is the df over du in this case? That's right. So this is the hint I gave it to you. Right? 1 over 1 plus u squared. And partial u over partial x here. Right here. What do you treat y? You treat y as if it is a constant. So I guess everybody knows, maybe if I give you 2 over x derivative, everybody should know that, right? Yeah. So in this particular case, what should I put it here? Y over and negative. Okay? Very good. Good. So this is the first derivative, right? And I think now this is where, you know, differentiates u from others. You don't leave it like this. Simplify it. So put the u back here. Okay. Was that correct? Yeah. Yeah. I guess everybody can put u back here, but not everybody can do the next step. So simplify it. Okay. You don't leave it like because if you leave it like this, then you start to take the second derivative with respect to x. Guess what? This is going to be very messy, right? Yeah, you got to simplify it. So you don't take a partial derivative of this with respect to x immediately. So simplifying it, meaning here, what's this? This is 1 plus y squared over x squared. So this is actually this, right? Yeah. Okay? Yeah. That make sense? No? Why not? Yeah? not because I see why not. Yeah. See, yeah, right? So you really get to this. This is actually, because, or maybe, what does this equal to? Okay, right? Yeah. So bring this x squared up to here, right? Okay. Now this is one thing I mentioned in the previous lecture. A over B over C, that equal to what? AC over B, huh? Yeah, not A over BC. Yeah. Okay? So, this cancel, you end up with, okay, that's much simpler, right? Yeah, much neat, brief and clean. Okay, so negative y over x squared plus y squared. So then you're ready to take second order derivative. Okay, second order derivative. So second order derivative meaning this one. Okay, and meaning taking second order derivative like this. Right? Like this. Okay? Yeah. So I think this is okay. This is again, you're taking respect to x, so you treat y as if it is a constant. So if y seems to messing around with your brain, with your mind, you can replace the y really with a constant, right? And then you replace it back, you know, when you're doing derivations. Okay. So this is basically first year you learn in the first term. You can use the quotient rules, right, to do this kind of a derivative. Okay. Yeah. So what do we end up with? Actually, you don't need you only need the quotient rules. Okay. Okay. So quotient rule meaning the square at the bottom there, right? And you can also use product rule. That's fine. Yeah. Right. Then derivative of the first one, derivative of the first one with respect to x, and that's 0. And then the second here, okay? What was that? Yeah, that's right. Yeah. Yeah, tell me, what should I put here, actually? 2xy. 2xy? How did you get 2xy? Yeah, well, anyway, so let me just u over v there, right? So u prime v minus u v prime over v squared, right? What's the u? U here is negative y. And v is x squared plus y squared. Is that right? Yeah. So u prime is 0. So there's a negative, right? Negative here. Negative u is negative y, and v prime is derivative of this, which is 2x. Okay. So negative negative cancel each other. So 2xy over x squared plus y squared squared. Okay. Yeah. So that's the second order derivative, partial derivative of f with respect to x. And you can basically carry out the similar calculation for the partial derivative with respect to y. Okay, so you'll end up with this answer here. It's the opposite of the df over dx second order. Okay? Yeah, you end up this. So basically, which means the original function, okay, this original function, this arctan y over x, satisfy this equation. Okay, so satisfy this equation here. This is a very important equation you will see in your next 2 years, okay, in upper year course. Okay. This is basically in incline only 2 variables. More general, there's another one, df over dz squared. Okay. This is called a Laplace equation. Yeah, you will see the name Laplace and Euler almost everywhere. Okay, so this is called a Laplace equation. As we're going to learn in the future, you will see that we can define ourselves a operator. Okay, we can define ourselves an operator like this: del square equal to this. Okay, yeah, this is called Laplacian operator. In fluid mechanics, okay, there is a concept called flux density of a gradient flow of a certain function. Okay, so for example, you have a fluid flowing, and then there is this basically velocity, right, representing the flow of the fluid at every point. Can you imagine that? Okay, so the velocity at every point, okay, in the 3D space representing the flow of the fluid is actually basically vectors. You know, at here it's flowing that way with this much strength. At there it's flowing this way and with that much strength. Okay? Yeah. So all the vectors, imagine that it's basically like a bunch of porcupine arrows. So you would imagine. So what's the density, you know, of this whole bunch of arrows, right? It's somewhere it's a little bit of the sparse, some other where it's denser. So that quantity essentially could be calculated using this Laplacian operator here, right? Yeah. And solution of the Laplace equation has a lot to do with the thermal, the temperatures, you know, and fluid type of application. Is that good? So bear this in mind that we may come back to this Laplacian in the future. Okay? All right. I just need to point out particularly we actually already used a chain rule already, right? This chain rule. So let me just specifically write down the few chain rules that are here. Okay. So we have been using them, but not really officially introduced them. So just officially some chain rules. Okay. There are a couple of rules here, but I think most of them are. One of them is pretty simple. You actually seen it already. Okay. So rule number 1. Okay. If we have a function of I'll use function of two variables as an example here. Okay. Then x probably is function of t, y is probably a function of t. Okay. So if you're looking for df over d, okay. So if you sub this x of t into this, y of t into here, so that function instead of multivariable function ultimately will turn into what? A function of single variable in terms of t, right? Now, so if you're looking for df over dt, so straight to d, okay, then how do we relate that to the partial derivative? So chain rule, so partial f over partial, okay, x first, and dx over dt. Partial f over partial y, and dy over dt. Okay, dy over dt. Okay, that's a simple chain rule. Okay, yeah. Let's say rule number 2. Okay, if we have a function of two variable, and x not just a function. Now let's say maybe if x is a function of two other variables, and y is also a function of two other variables. Right? Yeah. So for example, maybe x equal to u times v, or y equal to u squared plus v, like that kind of thing. Then, if you're looking for dz over du, right? When you substitute x and y here, the function f ultimately will be a function of u and v. Then df over du or dz over du will equal to, okay, dz over dx first, then partial x over partial u, and partial z over partial y, and partial y over partial u. Okay? Yeah. Okay? And if you can extend it very easily, if this is a function of three variable, x is u, v, w, you know, like that, just keep adding things out here, okay? Keep adding terms. Okay, yeah. Okay, that's basically the two kind of rules that you need to stick to in terms of the partial derivative, okay? Yeah. Now, I do want to mention one thing, but if I don't mention it, it's probably okay. Probably 99.9% will not make this mistake. But if I mention it, you might make this mistake. So, but it's a very trivial thing though. So you see here, right? Partial z over partial x, and partial x over partial u. So now some of you may think, look, there's a partial x, right? Can we cancel these two? Right? Yeah, that's a very tempting thing to do. Okay, so the answer is no, don't cancel it, okay? Yeah, don't cancel it. If you cancel it, what happened? What would be the right side? Okay, it's doing this. Apparently not right? So basically, partial x. But remember, for function with van variables, okay, when we have this, what is the df over dt? What do? We do this, right? df over dx, and then dx over dt. So in this case, look at that. Can you cancel this? That you can, right? That you can. Okay? So this straight d you can cancel. But this partial one, okay, you can't cancel. So this is just a symbol here, okay? So basically, this is not a quantity. If it's a quantity, you can. If it's a mathematical quantity, a 3 or 4, you can cancel that. This one you can't. This small dx mathematically represented as a infinitesimal small quantity for the x, right? That's dx, okay? But not this guy here, okay? Yeah. So now you know it, and don't try to cancel it. Okay. All right. So let me just see how's my timing doing here. Yeah. Now this is particularly long lecture notes, but a lot of things, if you think about it, they're actually not that new, though, right? Yeah. Let's try another example of partial derivative. Okay, then we can move on to a new concept. Okay, let's try this chain rules here. We have a temperature function. Okay, got a factor function, and we're going to have this relationship. Okay, as we're going to see in the near future. X equal to r cosine theta and y equal to r sine theta. You actually probably learned this in your early classes. This is actually, if x, y represents a point in Cartesian coordinates, then this relationship here, r cosine r theta here, that's actually basically in terms of so-called what? Polar coordinates. Okay? Polar coordinates. Okay, that's r and theta. So let's use the chain rule, but what we want is we want to calculate dt over dr. Okay, dt over dr. So you've got to be comfortable with which rule that you're going to use, right? In this case, I think we're going to use the rule number 2, right? Rule number 2. Okay. So this is actually not bad. Rule number 2, which means dt over dx first, and dx over dr, and dt over dy, and dy over dr. Okay. So, calculate each one of them. dt over dx. Okay. dt over dx, this is a function. You treat y as a constant. What do we end up with? 2x. Treat y as a constant. Yeah, this is where I see a lot of mistakes. A lot of times, sometimes people write as they write x at here. So really you should write y, right? Okay. And this one is constant, so 0 is gone. And then dx over dr, so this is x. So dx over dr, you treat theta as a constant. Basically, you treat cosine theta as a constant. So dx over dr is simply cosine theta. Okay. dt over dy, you treat x as a constant now. So negative x, 3y squared. Okay. dy over dr, so sine theta. Okay? Yeah. So you end up with an expression. You don't stop here though. You end up with an expression of mixed x and mixed x, y, and theta. Right? Yeah. You have a question?
So, with the second part of the description there, dx over dr, right? I know you're taking the derivative like the 2x minus y, but with like as a partial derivative of r, does y also have an r in it?
Yes, that's what we're going to do actually next. So what do you do with the xy? We substitute this xy into here, here, here. Okay? So basically, in the end, you have everything in terms of the r and theta. Okay? So what do we have? If I plug x here, y over here, so 2r cos theta minus r sine theta and cosine theta. Sorry, did I make a mistake here? Oh, actually, yeah, I didn't make a mistake. Oh, sorry, in my lecture notes it's a cube, but I use a square. But anyway, let's use this one here, that's fine. Was that okay, right? Yeah.
Aren't you like aren't you taking the derivative of r cos theta, so it should be negative sine? Like when you take the partial x over partial r?
Yeah, you're taking partial x over partial r. It's not partial x over partial theta. So, see, this quantity.
So r, yeah, okay. So r, so, okay.
Right? Yeah, what do you treat this one here? Constant, right? Yes. That's where this cosine theta is from, okay? Yeah. Okay, so plus negative r cos theta plus 2 sine 2r squared sine theta squared and then sine theta. Okay? Yeah. So in the end, I think your chances are you should expand everything out, right, and look at if there's anything that you can do to simplify it. Right? Yeah. During exam settings, it's too busy, that's okay. Just leave it as it is. That's fine. Okay? Yeah. Was that clear? Okay, good. Yeah. So I think you should try this. You should try what's d theta, dt over d theta. Okay? You should give it a try for this one. Okay, so was that okay? Yeah. So a couple minutes. I'll give you a little more training exercise out of here. Okay? Yeah. Still partial derivative. Okay. Still chain rules. So this one here is basically it's a function of two variables here, right? Yeah. I'll write it on the answer. You can, if you have done it, you can compare. Oh no, sorry. Actually, you know what? My lecture notes are different from this example, so forget it. You can try it yourself. Now, the question here is, can you calculate this? Can you calculate partial t over partial x and express this? Okay, express this using r and theta. You see what I'm saying? Okay? So calculate partial t and over partial x, okay, in r and theta. Because if I just let you calculate partial t over x, that's kind of too simple, right? Yeah. And then you express that in r and theta. It's actually not that bad, actually. So maybe this is x squared, this, right? Yeah. So I want you to use the chain rule right here to do it. If I want you to use the chain rule, what would that be? So there will be dt over dr and dr over dx. Excellent. And then dt over d theta and d theta over dx, right? That's the chain rule we set it here. Okay, the chain rule we set it. Now, this is actually, for this question, if you're going through along this route, it's actually a little bit more complicated, okay? But it's a good practice though, okay? It's a good practice. Technically, you don't need to go through this route. Technically, what you can do is, because you have already x squared minus 2x plus 2y, so technically speaking, what is the dt over dx? That's just the 2x minus y, right? 2x minus y. And then you sub the x and y into here, you get a function of r and theta. Does that make sense? Right? Yeah. But if you use the chain rule, you're going to have to use this. So the question here is, how do I calculate this using the chain rule here? Because what we need is, if you look at this one here, we need a function, a partial derivative here. So what is r in terms of function of x, right? What's that one there? This one here. What about this one here? Okay? So that's the question. Okay? That's a little bit more challenging if you use the chain rule here. So what I want you to do is check out example number 7, okay, on the page 28 if you need help on this thing here. Okay? There is a hidden point here. This is basically called a transformation between two different coordinate frames. One is x, one is xy, one is r theta. Any question? Yeah.
And one question on you have the full textbook.
Oh, textbook. Oh, this is my lecture notes. Yeah, lecture notes. Okay. Any questions? Okay. Okay. Thank you.